In this section, we'll be discussing the basics of chemical bonding. We'll be looking at ionic bonding and molecular bonding. And ultimately, the idea here is that this bonding involves the interactions between electrons from one element to the nucleus or the protons of another element, and how those things are interacting, or how those are even being shared between the two atoms. We have to also look at electron configurations of ions, so when they lose electrons or gain electrons, and also we're going to do some accounting of those, the difference between the number of protons and the number of electrons, and determine the formal charges of different elements within a molecule. We're going to talk about Lewis symbols and how to create them and look at them, what happens with the ions for those, and Lewis symbols for molecules. We'll be talking about covalent bonds as well in terms of molecular bonds, the octet rule, multiple bonds, and how that looks in terms of electrons. We will discuss some of the energetics of bond formation, electronegativity and polarity. That is an important feature of bonding. And we'll talk about resonance structure and then classify organic compounds. So this is this whole section. We'll only cover a little bit of this in this current lecture. The chemical bonds are basically the attractive forces that hold atoms together, and the reason they're held together is because of that positive charge in the nucleus from the protons and the negative charge of the electrons in the outer shells of the element, and how those things are interacting with each other. So why do we want to study this? We study this because it's really the basis for all of the chemical reactions that are occurring. It allows us to make predictions on what kind of things might happen and why they might happen. We need to understand how we break bonds and how the new bonds are going to form and why those things are happening. First kind of idea I want you to think about and just to kind of recall from past lectures is I want you to decide which of these three statements is true. So first is breaking bonds will always release energy, breaking bonds will always require energy, or breaking bonds sometimes require energy, sometimes releases energy. The correct answer is breaking bonds always requires energy. Remember, if you think about this as someone holding your hand, in order to break that hand hold, you have to use energy to pull those hands apart. But when you put those back together, then that will actually release energy. So bond breaking requires energy. The formation of new bonds actually generally will release energy. I want to first introduce you to this idea of covalent bonds versus ionic bonds. Now, covalent bonds, you can kind of see in this figure where we have these different shells of electrons. The valence shells electrons are actually interacting with both of these different nuclei, so they're kind of overlapping. So we'll have this covalent bonds occurs in molecules, and it involves the sharing of electrons between different nuclear centers. However, ionic bonding is going to occur in ionic solids like salts, and the electrons will actually be transferred from one element to another. For example, sodium is going to lose an electron to chlorine, and that's a transfer. So it is more associated with this chlorine element, the electron is, than the sodium. But because now there is an overall charge of the chlorine as a negative charge and the sodium is a positive charge, they will have still this kind of interaction or attractive force, but the chlorine is no longer sharing the electron with the orbital within sodium. So it's another way to look at it. It's a little more simple in terms of how these things are happening, and we'll look at this ionic bonding first. Ionic bonds result from attractive forces between oppositely charged particles. These are generally going to be between metals, like sodium, and nonmetals, like chlorine. So if you remember the periodic table, there's this line kind of diagonally from boron. Things on the upper right side are going to be nonmetals. Everything else is a metal. and those are when we are going to generate ionic bonds. Metals have low ionic energies or ionization energies, which means that it doesn't take a lot of energy to pull off an electron. So they're easy to lose electrons. Nonmetals have an exothermic electron affinity. So the affinity part is for them to pull electrons toward themselves. And we can kind of get an idea by looking at the electron configuration between sodium and chlorine. So if you look at sodium electron configuration, you'll notice that we have 2 electrons in the first shell, and we go into the 2s and 2p. So we have these electrons in the second shell. We go into a bigger shell, the 3s shell, and there's 1 electron out there. So sodium, this really far away electron, is easy to pull off. That's why it has a low ionization energy. Chlorine, for example, we're in the 1s, 2s, and 2p. We get into the 3s shell, and there are a lot of electrons in here already, which means there are a lot of protons that are attracting all of these electrons. And we have these things, we have this 1 electron out here, and it doesn't take a lot of energy for this electron, for example, to hop in here. All of these other electrons are already in this outer shell, so it's just 1 extra electron in there. It's actually a very exothermic electron affinity. Chlorine really likes to fill that spot up with another electron. So the other thing that we'll talk about is the formation of lattice energies. The lattices stabilize this, and I'll talk to you about that in just a moment. So here's the first kind of step here, the ionic compound, just as I showed you before in that last slide, where that sodium, 1 of those electrons will remove here. So this electron from the 3s orbital will bump down and leave this element and can be attractive to the chlorine element. So then we'll have a positively charged sodium, negatively charged chloride ion, and this is then an ionic bond between this positive and negative ions of this compound. Why does this occur? Why is the electron transferred? Why sodium plus and not Na2 plus or Na negative, chlorine negative, or -2 or a plus? Again, this all goes back to this electron configuration, and if we had to add another electron, it would have to go into a higher energy electron orbital, and it's just not going to be a very stable element. Chlorine, for example, doesn't want to necessarily lose this electron because there's a lot of positive charge, right? Remember, we talked about that net effective charge that these electrons are seeing, and it's seeing a really positive charge coming through these initial 2 shells. So there's still a really positive charge. So pulling one of these off is going to be relatively expensive in terms of energy. This is also one of the other parts of this idea, is this lattice structure. We get this lattice, we know that this exists in a 3-dimensional structure, and these elements are going to have some amount of interaction with each other, and they're going to form these kind of ionic bonds between them that help to recover some of that energy of transferring those electrons over. So when we write ionic chemical formulas, we always are written as empirical formulas, where the smallest whole number ratios of the cation and anion. So we've practiced that in past class sections. So 2 different pathways to evaluate this energy. First, we're looking at the sodium and releasing an electron, so the ionization energy of sodium. That's actually going to cost us 495.4 kilojoules per mole of energy. So we have to put in that amount of energy to rip off that electron from the sodium element. However, when we are going to add an electron to chlorine and we make a chloride ion, that actually releases energy, 348.8 kilojoules per mole. So is this energetically favorable? Well, right now, with just the ionization energy and the electron affinity energy, we'd actually say this was not favorable. It actually we would have to still input some amount of energy, 150 kilojoules per mole overall, than what we'd get out. So this wouldn't be actually energetically favorable at this point. But what we have to do is we actually have to add the lattice energy. So there's a certain amount of energy when we have a sodium ion and a chloride ion in close proximity to each other. They will make this ionic bond with each other, and that will actually release extra energy in that system if they're able to interact with each other. And here, then, we will have an overall difference of negative 411 kilojoules per mole. So now this is actually very energetically favorable, and it releases a lot of energy into the environment. And here's an idea of what's going on and how this lattice energy works and where this energy comes from. Right, so on the left side we have gaseous sodium chloride. On the right we have a solid crystal sodium chloride. So where does this energy come from? Remember, we're talking about when these are in a gas stage, they have a lot of kinetic energy. They have rotation, translational, vibrational energies. But when we move over here in this lattice, we've lost all of that energy. And the potential energy of the system is decreased when the solid salt is formed from the gas phase. So this actually is that decrease in energy is going to be a release of the energy from the system into the environment when that lattice energy is formed. In order to better understand this lattice energy, I want to introduce you to Coulomb's law, which describes that energy. So here we have the equation where energy is equal to a constant, which basically helps us convert charges into energies for this sake of this equation. And Q1 is the charge of the first ion, Q2 is the charge of the second ion, and then R is the distance separating the two charged ions. So let's look at a question that utilizes Coulomb's law to get a better understanding of what this means. So let's say we're looking at the separation between cations and ions in a lattice that is nearly identical. So that separation, we're pretending that R is about the same. Which species would have the greatest lattice energy based off of this equation? So the first step is to look at the different elements in here. We have the metals on the left always that are going to be positively charged, and the nonmetals on the right that are going to be negatively charged. And we're going to want to decide which elements have which charge. So we're just looking at sodium and calcium for the cations. Sodium is going to be a +1 charge. Calcium is going to be a +2 charge. Those are in the first two rows, first two columns of the periodic table. And then chlorine or chloride is going to be a negative charge. And the sodium, remember the crisscross rule, the nitrogen, remember the crisscross rule, the nitrogen will be a -3. And so we have oxygen is going to be a -2. So where is this energy going to be the greatest? This is where, and we're assuming R is equivalent and K is a constant, so that'll be equivalent. So we're really just looking at how can we get the biggest numbers out of the charges. Sodium is a 1, chlorine's a 1. Nope, that's not going to be it. We have a 2 and a 1. We have a 3 and a 2. We have a 1 and a 2 and a 2 and a 2. So the 3 times 2, that's going to be the biggest energy. So that's going to be the highest charge, and where these values are going to be the largest. And then that's also going to lead to us getting out the biggest energy. All right, here's another question. So which combination below will have the most negative lattice energy? Again, looking at Coulomb's law, where the energy is equal to a constant multiplied by the charge of the two elements multiplied by each other divided by the radius. We want the highest charged ions separated by the smallest difference is going to give us the largest lattice energy out. So here again, the lattice energy is essentially equivalent to the charges multiplied by each other divided by the radius. So the smallest radius, that's going to be dividing by the smallest number and allowing these things to remain high if we have the highest charged ions. So as Q increases, this delta H lattice increases. As R increases, as this becomes bigger in the denominator, then this overall lattice energy would decrease. So now we have a little bit more information regarding why metals form cations and nonmetals form anions. And it really comes down to this Aufbau principle and electron configuration. So let's look at, first of all, one of the big things is that this n value, the principal quantum number that describes that shell, that size of the shell for the electrons, is going to be really important. So let's look at an example of chlorine. And here we have the electron configuration written out. And we have these, we can also simplify this as the noble gas configuration. We have one spot. Remember, p orbitals can have 6 electrons because p, we have that pin shape. It has 3 orientations in the x, y, and z axes. So we could have up to 3p6. If we add 1 electron, we get the noble gas configuration. Right here we go from 5 to 6 of argon. It doesn't take that much more energy to add an electron. So that's typically why chloride will become a negatively charged element. And it doesn't take that much energy to do that. However, if we're looking at sodium, we wouldn't necessarily want to add another electron, especially when we're thinking about that effective charge of that element. So again, we have this 1s orbital with 2 electrons in it for here. And then we're going to add another bigger shell on the outside of that, where we're going to add that 2s electrons. And we're also going to get the 6 electrons in the p orbitals here. Then at the very end, we're also going to now create one more bigger orbital on the outside, which has this 3s, this 1 electron out here. Now the effective charge in a sodium element, if we have 11 protons in that nucleus here, we know that we have 10 electrons in the core, and that is going to be, right, the 6, 7, 8, 9, 10 in the core. So the effective charge that this element's seeing is 1 plus 1 charge. But that's not very strong. It's just a plus 1 charge. It's not like we have a plus 2 or plus 3 or plus 5. So there isn't very much strength in that charge. It's kind of like a really weak magnet. So we're able to pretty easily remove that electron. And then you can see here, once that electron's eliminated, that noble gas configuration looks just like neon. So we are then left with those core electrons as the size of the element. So if we start digging too much into this layer, into the core, now we can see that effective charge is going to be a lot higher for these electrons. Remember, because the elements in the same principal quantum number shell, those are going to be feeling that same effective, that charge. So if we have 11 protons are still in here, and we are only being shielded from the inside by these 2 electrons here, we would actually have effective charge of a plus 9, and that is going to be a lot harder than to pull electrons out of that those core shells. So this is kind of the end of how many electrons we really pull off, but this is stable still because removing that 1 electron wasn't that hard. Removing additional ones are going to be much harder. So I just wanted to look at the energetics of that in terms of kilojoules. That first ionization energy, the first electron pulling this first one off, is only 500 kilojoules per mole. It's pretty small, not too hard. But if we want to start digging into this 2p6 orbital, for example, then it's almost 10 times more difficult, 10 times more energy is required to pull that electron off. So the first electron can move pretty easily. The second one, that's not going to happen. Here's an example of an element from the second column, calcium. This is the electron configuration of calcium with the argon in brackets, and then we're in the 4th shell. It's an S2, is the 2 electrons in that shell, and ionization energies are not high, where it's about 590 and then about 1000. So it's still getting higher as we pull off that second one, but it's still manageable. And if we now go into these core shells in the 3p6 orbital, for example, in argon that would be in here, now this energy gets quite a lot higher. So it's about 5-fold more energy required. We can regain about 2,000 kilojoules from the lattice energy if we're at a +2 element. That recovers this initial ionization energy, but it's not going to be able to be recovered with this ionization in the third one. So the third electron is too hard to remove. We're not going to recoup that energy through the lattice energy. So calcium, a +3 calcium doesn't form. So some generalizations for this electron configuration for ions. When ions form, the S and P block ions tend to gain or lose electrons to obtain the nearest noble gas electron configuration. So they're trying to get to that noble gas configuration. That's generally going to give you the best idea of where the ionization energies are going to be most favorable, or electron affinity energies are going to be most favorable. The octet rule is this idea where we tend to gain or lose electrons until they've achieved an outer valence shell containing an octet of 8 electrons. Again, that is going to be from the s orbitals, which allow you to have 2, and the p orbitals, which allow you to have 6, and those are going to be 8 electrons. And remember that when we're talking about putting these are the only ones on the outside. The d and f orbitals, those are going to be core electrons, and those are not going to be part of the valence shell. So this is why the octet rule works, and this is maybe if you've done this in biology courses, we're always talking about 8, even though you think about those higher energy electrons, the D and F orbitals are higher energy orbitals, but they're shoved back into the core, so those are not accessible for chemical reactions. The octet rule works really well for metals in the first and second columns. It doesn't work as well in the transition metals because of some of the more complex things that might happen where electrons might hop around into different orbitals to create some stabilities. Also, obviously, hydrogen and helium can't obey that because they're in the upper shell here. They are only in the 1s shell, and you can only hold 2 electrons in there. So those are going to obviously create an issue. You're not going to have 8 electrons in an s orbital. So it doesn't work with the transition and post-transition metals, and we're going to talk about that next. But before we get into that, I just want you to look at this question and answer this, bring it to class, or post it in our Blackboard space. In the next section, we're going to start talking about transition metals and how to figure out what the possibilities would be, or why these different elements tend to give us certain types of ions compared to others. And this is going to really start to think about if we're completely filling if we're completely filling different types of suborbital shells, or half filling. Remember, I talked about that in the last section, where that creates some stability. So this is it for now, and the next section we'll be getting into this idea with transition metals more.